All right, everyone, welcome today. We've got Margaret Lumley going to talk about development of the desalination battery for energy efficient desalination and resource recovery. A couple things before we get started. One, this meeting is being recorded and we will post it on the NAWI Alliance community website as soon as possible after the event. Everyone is joined in listen only mode. That means you will be muted throughout the duration of the presentation. We highly encourage questions though, and please submit those to the Q&A box and we will address those at the end of the meeting.
Wait a minute, Ryan, it says the chat box. You say Q&A box?
Q&A or chat box, either one.
Okay, either
we will
one.
be monitoring both.
And do that as the question comes to you. You won't be interrupting, and it's great to just make sure that we gather all those questions while everybody, has them fresh on their mind.
Absolutely, thanks, Peter. If you have any audio issues, try connecting through your phone, or if you have any other technical issues, please reach out to me and I will help you work through those. Over to you, Peter.
Indeed, if you could relinquish the talking stick, I will share my slides. Everybody, thank you so much for coming today. As I said, it is our inaugural webinar for 2023, and a special one because we have in the house Dr. Margaret Lumley. Margaret is the co-founder and CEO of ChloBis Water. You will learn today the exciting frontier that she and her team are working on. She got her BS in chemistry from the University of California at Santa Barbara, with a PhD at University of Wisconsin-Madison, where she is now. Correct, Margaret? You are in Madison today. Very good. But very important, Margaret and her team are part of the Activate program. Margaret is an Activate Fellow in 2022. In fact, you can find her bio here on the Activate website. And the reason I want to introduce Margaret and also talk to you about the Activate program is the Activate program is an ideal mechanism for early career scientists to accelerate the commercialization of great ideas. And the Activate program is also sister to a program that was started by the Department of Energy called the Lab Embedded Entrepreneurship Program. So both these programs are operating right now. Both of them take applicants typically in the fall. The Activate programs are now in 4 different sort of sites. There's an Activate Boston, an Activate New York, and an Activate Berkeley that normally is known as Cyclotron Road. This was the origination program at Lawrence Berkeley National Laboratory. But Margaret is in the latest sort of virtual cohort, which is called Activate Anywhere. And Margaret, you look forward to hearing from you about how that works and what you are doing. But these are the Activate programs, and the Lab Embedded Entrepreneurship programs, the sister programs, are also at NREL, at Argonne National Lab called Chain Reaction, and Innovation Crossroads at Oak Ridge National Lab. In both cases, they're providing very similar things. So the LEAP programs provide a 2-year paid fellowship, like a postdoc essentially, with healthcare benefits, and very valuable for many technology teams, access to equipment and scientists at the national labs, along with the travel allowance and mentorship programming and an ecosystem. There's also an annual demo day. Activate has very similar offerings, but these 2 programs essentially are operating in parallel and largely providing the same thing. The goal is to help early career scientists who have promising breakthrough commercializable technologies get access to resources and facilities that startups don't normally get access to. This is Margaret's cohort for Activate this year, and you can see a lot of these people, including some people from your institutions. Now, I will just wrap up before I hand over to Margaret, that after this, we will have another webinar on January 25th with another Activate cohort member. This is Daniel Sun, and Dan is at Lawrence Berkeley Lab as an Activate Fellow in Cyclotron Road on another water treatment technology. So you can see water treatment technologies are definitely within the envelope of Activate. So Margaret, thank you so much for coming today. And I'm going to stop sharing my screen and invite you to take over at this point. Thank you so much. And maybe you've been in the Activate program how long? When did you get started?
June of this year, so coming up on 6 months. It's a really great program, highly recommend it to any founder working in really any clean tech arena, and happy to talk more about the program if you're interested. My email is up on the slide here, and then it's on my last slide as well, so feel free to reach out.
Thank you so much, Margaret. That's great, and take it away. Thanks so much.
Wonderful. It's great to be here today. Happy New Year, everybody. As Peter mentioned, my name is Margaret Lumley, and I'm the CEO and co-founder of ChloBis Water. and we're located in Madison, Wisconsin. And today I'll talk to you about our new desalination battery that we're using for energy efficient water desalination and resource recovery. Just to give you a brief agenda, I'll start with an introduction and then talk more about our technology and the way that we've developed our electrodes. I'll talk through a few different applications that we're currently pursuing, and then end with a little overview of where we are today and where we are headed. And before I get into that, I just wanted to talk a little bit more about my background and how I got here to be the CEO of ChloBis Water. As Peter mentioned, I went to undergrad at UC Santa Barbara. I'm originally from the East Bay, just over the hill from Berkeley. And I got my start in research working in a group on lithium-ion batteries. So really got my first taste of electrochemistry and fell in love with the field. I did an internship in college at Trinity College in Dublin, Ireland, where I worked on carbon nanotube membranes for reverse osmosis. And then I ultimately came to UW-Madison to combine those two interests, electrochemistry and water treatment. And while I was in grad school doing my PhD, I became really interested in technology entrepreneurship and the idea of working at the intersection of science and business, and figuring out how to take these cool technologies that are invented in on-campus research labs and try to actually turn them into commercial products. And so that's where I am today. This audience probably doesn't need this slide, but it's become more and more evident that water scarcity and addressing water shortages is one of the main challenges of the next few decades. And currently, about 66% of the world's population lives in conditions of water scarcity for at least 1 month of the year. And this problem is continuing to get worse. When I talk about water scarcity in Madison, it doesn't actually feel top of mind to most of us. We have a lot of water here. We have the Great Lakes. And so it feels like a very far away problem. But growing up in California, going to college in Santa Barbara, water shortages were really a part of my day-to-day life. And when most people think of Santa Barbara, they think of this beautiful aerial photo where we have the campus right next to the ocean. And this is an accurate depiction of our college. But we also have really severe droughts in Southern California. And I'm showing on the right here an image of the Santa Barbara County Reservoir in 2011 when I started college, and then in 2016 when it was almost entirely depleted during the drought. And we all know that California and other states in the West are in the midst of a mega drought. And so the idea of desalination is really thinking about how can we turn this ocean water that's so abundant into something that can fill these reservoirs. The Earth is actually covered in water. About 70% of Earth's surface is covered in water, but most of that is ocean water, which we can't drink, and less than 1% of water available on Earth exists as fresh water. And so when we think about desalination, it's really this process of removing ions from any water source. And I'll start by talking in the context of seawater desalination, although there's other types of desalination as well. And so really we were motivated thinking about how can we turn ocean water into fresh water. And before we started working on our own technology, we wanted to understand what is currently out there today. I'm showing some really simplified schemes here of the most common desalination methods, which are thermal distillation and reverse osmosis. Distillation relies on heat energy to boil saline water, followed by recondensation to generate fresh water and leave the salt behind. And today, distillation accounts for about 25% of global desalinated water production. It's very energy intensive, and so construction of distillation plants has slowed down in the past few years. Reverse osmosis is the dominant technology that's used today for seawater desalination. And in RO, a high pressure pump is used to force water through a semi-permeable membrane that allows water to pass through but rejects salt. So in RO, you produce a desalinated water or freshwater stream, but you also produce a concentrate or brine stream that needs to be disposed of. And the way that's traditionally done is it's pumped back into the ocean through a brine outfall. Today, about 70% of global desalinated water is produced through reverse osmosis. These two methods are really well established, but they both have some limitations, some challenges, which I've highlighted that need to be overcome as reliance on desalination continues to grow. And so as an electrochemist, one strategy that we can think about to remove salt ions from water is electrochemistry. Electrochemistry is used in conventional lithium-ion batteries. We know how to use electrochemistry to move ions around. And one of the dominant electrochemical desalination methods is electrodialysis, which uses membranes like reverse osmosis, but we use ion selective membranes. In electrodialysis, you have an anode and a cathode. When oxidation occurs at the anode and reduction occurs at the cathode, ions move through these ion selective membranes to produce this desalinated water stream. Using electrochemistry to drive ion movement through membranes is kind of the really simple way to think about electrodialysis. Electrodialysis has some intrinsic advantages when you compare it to reverse osmosis, but it actually requires a pretty high voltage to get these reactions to happen. And so currently electrodialysis is really only used for brackish water desalination, and only about 4% of global desalinated water is produced by electrodialysis. Another technology that some of you might be familiar with is capacitive deionization, where you use high surface area, typically carbon electrodes. And when you apply a voltage between those two electrodes, you adsorb cations onto one and anions onto the other electrode to achieve desalination. Ion removal in capacitive deionization is really limited to the surface of the electrode materials. And for that reason, again, CDI has really only been used for brackish water desalination. And so when we think about water desalination, the way that it's been changing over the past few years, we see this exponential growth in global desalination capacity, which is primarily dominated by reverse osmosis in blue here. And the reason for that is that the cost of reverse osmosis at some point competes or beats other desalination methods. This graph is a little bit outdated, but you can see that electrodialysis is more cost effective when you have these lower salt concentrations. But once you get up to the really brackish water and seawater range, reverse osmosis is always more cost effective than other systems that are currently available. And so what we've done at ChloBis Water, and when we started working on this technology, is really think about what are we trying to do when we desalinate ocean water? And essentially what we need to do is remove sodium and chloride from seawater. About 90% of salt in seawater is sodium chloride, same composition as table salt. And so to do this with electrochemistry, we need a material that can store sodium and a material that can store chloride. And we were inspired by intercalation type materials that are used in conventional rechargeable batteries as we began to work on this field of electrochemical water desalination. So once we're able to identify our sodium and chloride storage materials, we can combine them into a device that we call a desalination battery. What happens here is that the sodium storage material removes sodium through an electrochemical reduction reaction, acting as the cathode, and the chloride storage material removes chloride through an electrochemical oxidation reaction, acting as the anode. And in this process, our cathode potential is more positive than our anode potential. And really that matters because it means that this process actually generates electricity, produces a positive cell voltage as we're doing desalination. So reverse osmosis, distillation, electrodialysis all consume energy to remove salt from water, but our system actually produces energy as we're doing this desalination step. When our electrodes are saturated with sodium and chloride, we can move them to another solution, and we do this regeneration step, which we call salination. And so by supplying electricity, our electrodes reduce the sodium and chloride that we've removed from water, and we can produce a high concentration sodium chloride stream that you could then use for other industrial processes, things like food processing, road de-icing, anything that requires sodium chloride. There's 100 different potential applications. Because our device is selective for sodium and chloride removal, ideally we will produce this usable product rather than a brine stream, which is what we're producing with reverse osmosis and electrodialysis. This is another visual representation of our technology, which I'm showing because we can actually tailor this regeneration step to recover valuable commodity chemicals. On the left here, you can see the same desalination process that I just described. And on the right, I'm showing a variation of a resource recovery cell where we've added what's called a bipolar membrane that does water dissociation. And in this bipolar, or using this bipolar membrane, allows us to directly recover sodium hydroxide, commonly known as caustic soda, and hydrochloric acid, which have their own industrial uses. Hydrochloric acid is used in the steel industry for steel pickling, and caustic soda is used in a variety of industrial processes and for things like pH adjustment. And so the vision here is to develop this closed loop, energy efficient system where we can take salt out of one water source and convert that salt into a useful commodity chemical. This sounds great and simple enough. We were not the first people to think of this type of technology. And so I want to talk through what some of the challenges have been as we've started and continued to work on development of our desalination battery. Really, what we focused on is identification of materials and development of electrode processing methods for those materials. When we think about the availability of electrode materials for this desalination technology, we need to, as I mentioned, have a sodium storage electrode and a chloride storage electrode. Some of you might be familiar with research in the field of sodium ion batteries. It's a pretty active area of research. And there are, for that reason, quite a few sodium storage materials that we could evaluate, already known candidates that we could find from reading the literature. But chloride storage materials are actually really, really rare. Most metal chloride species dissolve in ocean water and in water in general. And before we started working on this technology, the only known chloride storage material was silver, which is too expensive to be used for practical desalination applications. And so the first step in developing this technology was trying to find an appropriate chloride storage material. My co-founder, Dr. Jawan Nam, in 2017 screened a variety of different candidates that we might be able to use as chloride storage materials, and he found that bismuth metal can be used as a practical and effective chloride storage material through the reversible electrochemical conversion between bismuth and bismuth oxychloride, which I'm showing here. We patented this discovery in 2017, and I'm showing in this table that bismuth is much less expensive than silver. And so we were really excited about this discovery, and it allowed us to really start to investigate the possibility of developing a practical desalination battery. When we first started testing bismuth as an electrode material, Jawan had the idea to develop an electrode deposition method to produce these high surface area bismuth foam structures to try to maximize our salt removal capabilities. And the first thing that we had to do is characterize our material to see if we're actually doing the reaction that we wanted to do. And so I'm showing here these X-ray diffraction patterns, which I'll go through pretty quickly, that just indicate that when we make our electrode, it matches with bismuth metal, this blue graph here. And then when we do the oxidation reaction in a sodium chloride solution, we do form bismuth oxychloride, which corresponds to these red dots. And then when we do reduction, we go back to bismuth oxychloride, and back to bismuth again. So really indicating that we are able to remove chloride using these bismuth electrodes. One thing that is really important when you think about electrochemical systems is long-term stability. And so to evaluate long-term stability, we monitor the salt removal capacity, which is on the y-axis here, as a function of cycle number, the number of chloride removal and release cycles that we're doing. And so even though we were able to prove that we made this bismuth oxychloride phase, we saw capacity fading within 50 cycles. We started to lose some of our active material really, really quickly. This is actually what happens in traditional batteries as well, and is the reason that you need to charge your battery more frequently as it ages. But this was not a great first step as we started to look at our new desalination process. And the first thing that we did is try to understand why we saw this capacity fading. And what we found is that during the conversion of bismuth to bismuth oxychloride, we actually have a volume expansion of about 150%. And so you can imagine as we continue to use this electrode over and over again, it's expanding and contracting and expanding and contracting. And we start to see sort of chunks, for lack of a better word, of the bismuth electrode fall off. And for that reason, we see this capacity fading because we're losing our active material. And so our next step in our development process was to try to find another way to make these electrodes so that they were stable for an increased number of cycles. And so the way that we did that was actually by starting with bismuth powder, which you can purchase, it's commercially available, and using a high energy ball mill to mix that bismuth powder with carbon as a conductive additive. And then we add a polymeric binder called PTFE, and we form this little ball that has the consistency of Play-Doh. And then we put that Play-Doh through a pasta maker, and we end up with these sheet type electrodes. And after we dry those electrodes, we cut out a little circle about 1 centimeter squared and put that electrode onto a current collector. This is kind of analogous to the way that you make conventional battery electrodes. And so using this new electrode fabrication method, we've created this carbon and polymeric binder framework around our active materials to kind of keep everything together. And when we look at these electrodes, we find that they're really, really flexible and robust. They have a really high mechanical strength. They almost have the consistency of a really thin sheet of rubber, but are very conductive. And so using these electrodes, we can now see stable performance of our bismuth electrode for over 5,000 cycles. We've gone up to 8,000 cycles now. These tests are actually running for over a year, and we see no performance degradation. So through this really intensive optimization process, we've been able to increase the lifetime of our bismuth electrode from less than 50 to over 5,000 cycles. And I'm kind of showing the highlight reel here, but this process of developing our robust electrode fabrication method has happened over the course of about 5 years, starting with the discovery of the bismuth electrode back in 2017, and now really starting to think about scaling up our electrode fabrication method and making these really large sheet type electrodes so we can ultimately build a prototype cell in the next few years. So now that we have confidence in our bismuth electrode, I want to switch over to talking about the sodium storage electrode that we use. And when you think about electrochemical desalination, one thing that makes it really complicated is that in any aqueous solution, you have the potential to do water oxidation or water reduction. And you really want to try to avoid those reactions if possible. They're always potential competitive side reactions. And so on this graph, I'm showing the electrochemical operating windows of a few different sodium storage electrodes in blue. And you can see there's quite a few that have this HCF termination that stands for hexacyanoferrate. And these materials belong to a class of materials called Prussian blue analogs, which are probably the most widely investigated materials for sodium storage in aqueous solutions. And so we decided to look at Prussian blue analogs as well. Prussian blue analogs have this open framework crystal structure, and they're made of these ferricyanide groups and a divalent transition metal ion like copper, nickel, manganese, cobalt. There's quite a few different types of Prussian blue analogs. The really important thing that I want to point out is because of this open framework structure, Prussian blue analogs can really easily intercalate and deintercalate monovalent cations like sodium. And they've shown really exceptional stability in acidic aqueous media, over 40,000 cycles with very little loss in capacity. There's also, like I mentioned, a wide variety of compositions, which means we can sort of tune the properties of Prussian blue analogs. But as I mentioned, other research groups have also investigated the performance of Prussian blue analogs for desalination applications, where you have a neutral aqueous solution. This plot on the left is actually one of our previous papers where we looked at using copper hexacyanoferrate, and we saw capacity fading within about 40 cycles. Here are some other types of desalination cell configurations that used Prussian blue analogs, and you can see in all cases capacity fading occurs within just tens of cycles. Long-term stability is really important for any real-world application, including water treatment. And so this idea that Prussian blue analogs are degrading over time was kind of discouraging. But when I was doing my PhD at UW-Madison, we decided to try to investigate why this was happening and see if we could find a way to make a stable Prussian blue analog that could be used for seawater desalination. And so we went back to the drawing board and we decided to choose nickel hexacyanoferrate as our electrode material because it shows the least overlap with the water oxidation potential, which is this dashed blue curve here. And I spent a long time during my PhD investigating different structural features. One thing that I looked at is the number of ferricyanide vacancies. So you can essentially have holes in your crystal structure, which affect the performance. Also looking at particle size. So how big are the particles that we're producing? Crystallinity, and then crystal symmetry. And I won't go through all of this work. I'll kind of skip to the end, which is the good result. But if you're interested, you can take a look at this paper that I published back in 2020. The reference is at the bottom of the slide. So ultimately, we were able to make this nickel hexacyanoferrate material that has this really, really nice cubic morphology, which I'm showing in this SEM image here, a really high crystallinity, which you can see from X-ray diffraction, and then ultimately shows stable performance in sodium chloride solutions for over 200 cycles. And this is the first time that a Prussian blue analog showed stable performance in these aqueous solutions. And another thing that we looked at is the ability or the effect of the rate of charging and discharging on the performance of our nickel hexacyanoferrate electrodes. So this is a really common practice in electrochemistry. You can change how fast you run your reaction, and that typically has an effect on the salt removal capacity. And what we saw here is that when we cycle our electrodes for 3 minutes per cycle at 20 C, we see almost the same capacity as when we cycle them for 25 minutes per cycle. So this is really encouraging and indicates this fast kinetics for sodium insertion and sodium release reactions that is important when we're trying to produce desalinated water on a commercial scale. And so when we make both our nickel hexacyanoferrate and bismuth electrodes through that electrode fabrication method that I showed on my previous slide, we can achieve stable performance with both electrodes for over 5,000 cycles. Again, over a year of continuous operation in these sodium chloride solutions that have a salinity approximating that of seawater. The other thing that we looked at when we did these experiments is the energy recovery efficiency. So I mentioned that our system produces energy during the desalination step, which you can see by this red curve here, and consumes energy during the electrode regeneration or resource recovery step, which you can see is this blue curve here. And so in our optimized system, we can achieve an energy recovery efficiency of over 90%, which is really encouraging. Another way to think about it is that our system is about 90% self-powered. And that's one of the really big benefits of this type of electrochemical desalination method. It's about 90% self-powered. We're also selective for the removal of sodium and chloride, and I'll talk about the implications of that selectivity in the next few slides. And ideally, we don't produce any brine waste, which eliminates brine disposal costs, because as I mentioned, the sodium and chloride that we've removed can be converted into usable commodity chemicals. And I like to show this image here from our lab taken a few years ago, where we immersed our nickel hexacyanoferrate and bismuth electrodes in a sodium chloride solution, and actually were able to see firsthand this power generation when we connected those electrodes up to a light bulb. This lasted for about 20 minutes, kind of a cool, fun benchtop experiment to do. And through the development of this desalination technology, we're combining the functions of desalination with energy generation and storage, trying to address challenges at the intersection of the water energy nexus, a mission that NAWI shares as well. When we think about, again, actually using this technology for seawater desalination, one thing that I want to come back to is the idea that seawater is about 90% sodium chloride, but there are all these other ions in there as well. And we cannot today remove those other ions with our desalination battery technology. And so if we were to use this system for seawater desalination, it would essentially be a tandem approach where we put seawater through our desalination battery, take out most of the sodium and chloride to make what's called brackish water, and then put that brackish water through something like reverse osmosis or electrodialysis to ultimately produce fresh water. As I showed in my introduction slides, the energy associated with reverse osmosis is proportional to the salt concentration. And so the ultimate benefit of using this type of tandem approach is that we would reduce the energy consumption and reduce the brine production volume. And so just to give you some rough idea of what that looks like with some numbers attached, in the status quo seawater RO system, we start with seawater, we make fresh water, we have at about a 50% water recovery, and the energy consumption is about 3.5 to 4 kilowatt hours per cubic meter of water. If we were to use our tandem approach with the desalination battery in combination with an RO system, we would have about an 85% water recovery, and we think we could reduce the energy consumption to less than 1 kilowatt hour per cubic meter. This has a really big impact when you think about these mega seawater desalination plants that are being built today, producing 1 million plus meters cubed of water per day. When you think about these large plants, even small savings in energy consumption can have a big impact on greenhouse gas emissions and operating costs, and ultimately cost of water produced. And the last thing I'll touch on is that in this section is that our technology is really well suited to integration with renewable energy. It is itself a battery. And so we could, during our desalination process, distribute electricity to the grid, use electricity to power pumps at the plant, really try to make use of the energy that we're producing during our salt removal step. And then when we do the regeneration step, we can directly use renewable electricity to power that process. Conventional desalination, like reverse osmosis, it's really hard to integrate reverse osmosis plants with renewable energy because of the high cost of energy storage systems. And so we think there's a really unique, interesting benefit of having this combined desalination and battery function in one device. And so thus far, I've talked all about seawater desalination, but we all know that there's a lot of different ways that we can use desalination technologies: brackish water desalination, production of ultra pure water, wastewater recycling, the list goes on. And so we've also started to look at other applications of our technology. And a few that I want to highlight here in this presentation are treatment of wastewater from food plants and municipal wastewater, and then also looking at brackish water desalination specifically for agriculture applications. And to learn about these different applications, I've gone through 3 different customer discovery programs, including NSF I-Core, and have conducted now over 300 customer discovery interviews, which sounds like a lot, but I'm still learning so much, still have a lot to learn about the field of water desalination. And so I'll start by talking about a local Madison problem where our technology might have some interesting opportunities. So I started this talk by mentioning that water scarcity is a huge growing problem. But in addition to running out of water, the water sources that we do have are actually getting saltier. And in the Midwest, we see headlines like these plastered all over the news on almost a daily basis, talking about how salt is polluting our freshwater ecosystems here in the Midwest. One of the contributors to that increasing salinity is the discharge of wastewater. It's estimated that about 80% of global wastewater is discharged to the environment without adequate treatment. And some of that wastewater contains salt, which comes from sources like road salt, water softener salt, and other industrial sources. And it's actually the chloride specifically in that salt that is causing issues. Chloride is really toxic to freshwater aquatic species. And to try to manage that concern, regulators in the Midwest have imposed chloride limits on wastewater treatment plants, which I'm showing in red here. A number of wastewater treatment plants are currently exceeding those chloride discharge limits, and they have what's called a variance permit. And one of the challenges here is that there's no cost-effective way to specifically remove chloride from water. And so these limits are pretty much practically impossible to enforce. Our local wastewater treatment plant, the Madison Metropolitan Sewerage District, actually reached out to our team. They saw a little news article about our technology and asked when it would be ready to deploy, because they've explored and exhausted all possible chloride removal options and are still unable to meet this chloride effluent limit, which is where we come in. They did this really comprehensive study at the Madison wastewater treatment plant to evaluate the cost of installing a reverse osmosis or electrodialysis system at the wastewater treatment plant. And what they found is that these systems had a capital cost of $80 million or more, but the primary barrier for the implementation of these systems in the Midwest has been annual brine disposal costs. So if you're near the ocean, you can put the brine back in the ocean. If you're in the Midwest, like we are, where we only have freshwater sources, there's no options for brine disposal. The best option that they could come up with was putting the brine in a truck, driving it to a state where fracking is popular, and doing deep well injection. And so trying to manage this brine is a huge, huge, huge issue for using reverse osmosis or electrodialysis in places like the Midwest. We've also looked at other areas that are suffering from high chloride concentrations in their wastewater, and food processing plants are a market that has been pretty significantly impacted. You can think of things like pickling, meat processing, cheese processing, which we have a lot of here in Wisconsin. Those processes all use really concentrated salt water, and that salt water ends up in their wastewater streams. And these food processing facilities are also facing chloride limits in their discharge permits. Again, really no great solutions available today to remove chloride from that wastewater effluent. And so something that we've thought about as we continue to develop our technology is using these food processing plants to demonstrate our chloride removal or desalination system at a relatively small scale, and then ultimately moving to municipal wastewater treatment and expanding into the seawater desalination market in the future. Seawater desalination requires the treatment of huge, huge volumes of water. And so we're always interested in smaller scale applications that we could target to try to demonstrate real world operation of our technology as soon as possible. And then another area that I want to highlight is looking at desalination of water for agriculture, which is a problem that is kind of more California focused, especially in the Central Valley, and then some coastal parts of California as well. Some of you might be familiar that there are kind of a few different factors that are contributing to increased salinity of water that's used for irrigation. Because of the drought, groundwater aquifers aren't being replenished with fresh water that typically comes from rain. And so that's actually led to salinization of groundwater aquifers. We also have this issue of seawater intrusion, which happens when you overpump a groundwater aquifer, and that allows salt water from the ocean to seep into those aquifers. And so we kind of have this confluence of factors that is leading to an increase in the salinity of water that's used for irrigation. And salty water has a negative impact on crop yield, which you can see from this image here. And California actually experienced a reduction in agricultural revenue of $3.5 billion in 2014 because of high salinity. There's really not a lot of great options out there to try to manage the effects of salty water used for irrigation. And one reason for that is that the cost of water used for agriculture is really important. There's some pretty strict price limits on what growers can typically afford to pay for water in order to remain profitable. And so I did this back of the envelope calculation using an example from a well in the Central Valley of California to find that using our desalination battery for this specific well would lead to a cost of water of about $435 per acre foot. And the cost of water for high value crops should be less than $750 per acre foot. So we fall within the range of what is affordable for growers. A commonality in this application is that reverse osmosis, again, is not a great option because of the production of brine waste. It's really expensive, thousands of dollars per acre foot to dispose of brine in a place like the Central Valley that is not near the coast. And so really trying to find ways to deal with this brine or minimize the production of brine waste from the beginning are kind of important things to consider as we try to develop desalination technologies for these other applications where the desalination hasn't been able to be used in the past. And I just want to end this section by talking about this specific example in Santa Clarita in Southern California, where a wastewater treatment plant was discharging their effluent to the Santa Clara River, which is used downstream for irrigation of things like strawberries and avocados, which are very, very sensitive to chloride concentrations. And in Santa Clarita, they went through this multi-stage process trying to reduce the chloride concentration in their wastewater effluent to meet this really strict limit of 100 parts per million, again, because of those downstream agricultural users. And they ultimately are having to install a reverse osmosis plant to manage that chloride concentration, which is costing upwards of $115 million. And this is kind of a California example where chloride itself is causing issues, especially for agricultural users. And I've highlighted the applications where we've really spent a lot of time learning about how our technology could provide benefit, but we're always open to other ideas where sodium and chloride are causing issues, or where brine management is really an important avenue to address desalination more feasible. And so where we are now is really in this transition period, going from our bench scale beaker experiments where we're testing high purity sodium chloride solutions to actually building these small scale devices that we will use to test the performance of our system in real water samples to evaluate things like scale formation, ion selectivity, the effects of organic matter, the effects of pH, the effects of salt concentration, really in this transition of, true bench scale experiments to actually more practical experiments that will ultimately help us determine how to deploy our technology. Our plan is to use the sheet type electrode fabrication method to make these little things that we're calling unit cells, which I showed on the last slide, and then ultimately to design a modular flow cell of about 50 liters per minute to demonstrate our complete desalination and resource recovery process at an intermediate scale. So far, we have published quite a few papers about this technology and different combinations of our electrode materials. We filed 4 patents. ChloBis Water was incorporated in 2021. We've had some great traction with federal funding, including an NSF STTR award, and I'm also a part of the Activate Fellowship, which Peter mentioned in the beginning. Earlier this year, we hired our first employee, and as I mentioned, we've conducted hundreds of customer discovery interviews, and we're excited to keep going. I founded ChloBis Water with two co-founders that I met at UW-Madison, Dr. Do-Won Nam and Professor Kyung-Shin Choi, who was my PhD advisor, both with really extensive backgrounds in electrochemistry. And Do-Won is the one responsible for really really helping us advance our electrode fabrication procedure and helping to achieve that really high stability that I've showed in the past slides. We've had some really great supporters along this journey as well, including some local facilities that have offered to pilot our technology once we get to that stage. And our vision is really to develop the desalination battery to make desalination accessible in places that it's not today. And my ask for all of you today is, we're always continuing to learn more about how our technology can be used, how to scale electrochemical systems. We're ultimately looking for investors in the next year or so, always looking for advisors and potential partners. And then if you're really, really interested in what we're doing at ChloBis Water, we're looking to hire another engineer in the next few months. So keep that in mind and send any potential candidates my way. And with that, I will open it up to questions.
Margaret, thank you so much. Applause, everybody. Great presentation.
Thank you.
Wonderful story to tell us the journey that you've taken so far in this. You've got a bunch of questions in chat and a bunch of questions in Q&A. And what I'm going to do is I'll have you kind of look through those and say which ones you think, given the time we have left, about 12 minutes. But I want to kind of touch one initial issue that several questioners kind of touched in various places. And that is that you're at the stage right now where you look like you have a very exciting unit process for separating the monovalent salts, et cetera. And then you discovered the water matrix, all the garbage in the other periodic table that is in most natural waters or even real world wastewaters. What are you learning so far about the water matrices that are either maybe additionally problematic or affecting how this system is going to be either requiring pre-treatment or somehow modifying it to be tolerant of certain other things? So what do we know about real waters?
Yeah, that's a great question. So far, what we have seen is no scale formation. So when we introduce calcium and magnesium, that's the biggest concern, is forming these scale layers, which we haven't seen, and that's exciting. We tested brine from a pickle plant, and it actually got moldy, which is very gross, but the growth of mold.
You mean mold in the electrodes?
Yeah. Didn't affect the performance, so that was great as well. Something that we need to investigate, especially for our nickel hexacyanoferrate electrode, is ion selectivity. So if we're removing calcium and magnesium in addition to sodium, that will affect the purity of the sodium hydroxide solution that we can produce. And that's kind of our next step with this prototype cell. The challenge that we've had that we didn't expect is that we see an upper limit to the concentration of water that we can treat with respect to chloride. So we can treat seawater, 35,000 parts per million, no problem. But once we get up to things like 50,000, 60,000, 70,000 parts per million chloride, we start to see some competing reactions occurring. And so we're not sure if that's, something that we'll be able to address, but that is one concern, is this upper chloride concentration limit. And that would be relevant if we were to think about directly treating water softener regeneration brine, for example, or trying to recover chloride from reverse osmosis brine directly. So just something that we have to be mindful of in the future. But for the most part, we've been really encouraged by the fact that we haven't seen these other issues, and we don't have a membrane in our desalination cell. And so that potentially provides some advantages in terms of pre-treatment that we won't need to do, unlike reverse osmosis. Yeah.
As you look through these questions, were there some other questions you thought particularly salient? Some touch each other, but some are interesting.
So one of the questions is about energy density compared to lithium ion batteries.
Oh, that's interesting.
That's a question that comes up a lot. In aqueous systems, your main limitation is the voltage that you can generate. Typically, you're limited to about 1.4 volts because water splitting occurs at 1.23 volts. Lithium ion batteries have a 3.5 volts. So we really can't compete when you're thinking about things like portable applications. You could think about like a stationary seawater battery, but energy density in aqueous solutions is always a concern. We wish we could produce a higher voltage, but just not possible given the complexity of water.
Yeah.
Another question was about, experimenting with very high TDS produced water, trying to treat produced water. We've thought about that too, but again, that high chloride concentration might be an issue ultimately. Organic compounds, a lot of questions about, real water samples, which hopefully I've addressed, but feel free to follow up if there's something more specific. Somebody asked about the actual electricity input that we need. So I didn't touch on this, but our system during the desalination step will produce about 8 kilowatt hours per cubic meter of water. The input that we need for regeneration is about 8.5 kilowatt hours per cubic meter. To give a reference point.
I have a sort of a general kind of comparative question. So if you think about, when you think about membrane technologies like reverse osmosis, you think about, LMH or, liters per square meter per hour, sort of like diffusivity kind of things. Is there, what's the equivalent kind of expression of how much membrane surface area you need per unit of water treated? And I imagine that may scale with the salinity, et cetera. So tell us a little bit about how we should think about the system requirements and the membrane surface area requirements for this.
Yeah. So one thing that we haven't done yet is test a flow cell. We're using these batch type systems and, real water treatment processes, you always use a flow cell. So you would think about something like meters cubed per hour, Peter, like you alluded to, or liters per hour, whatever. With our electrodes, to give you a reference, with a 10 centimeter by 10 centimeter electrode, we can desalinate about 300 milliliters of water in 10 minutes. So the idea would be to sort of have this modular setup where we stack these electrodes and ultimately devices together. There's questions in here about like footprint and rate of desalination, and those are all things that we're still trying to figure out, but really, really great questions to ask. When you think about a municipal seawater desalination plant, at least the ones that I've seen, there's a lot of open space around those facilities. So I think that for those larger scale applications, size may not be as important. But if we wanted to do treatment at a well in the Central Valley, for example, size would become really, really important, and ability to treat water at a sufficient rate. So good questions, things that are on my mind as well, but no great definitive answers at this point.
I think one of the things people may also give you advice on, and I've seen a lot of great comments from everybody so far, and including some volunteers for assistance. And that is, it is often the case that a very promising unit process technology at the bench scale often kind of comes up against real water matrices. And those things, that's why God invented pretreatment, is to bring the water into a compositional window that's going to be ideal for the unit process that does the ion separation. And so I would simply say, maybe people on this call or others have some advice as to how to proceed into those dark woods of getting up to real water matrices, and how not to break your teeth trying to do something with one matrix or one water type that might represent something that's way far down the road. And so I don't know, the devil is always in the matrix, and that is where we could maybe have some good advice from people here. Let me ask you, go ahead.
I was just going to say, one question that I saw in the Q&A is about the size of the market for sodium hydroxide and hydrochloric acid. And that's something, again, that is, kind of a matchmaking process that we're going through. We have these 3 technology features, for lack of a better word: desalination, energy production and storage and chemical production. And so really thinking about how do we optimize our system for which features. If we were to build a municipal scale seawater desalination plant, we'd be producing so much sodium hydroxide and hydrochloric acid. And sodium hydroxide is a little bit easier to manage, but hydrochloric acid or chlorine gas or bleach, whatever chlorine-based chemical you're trying to produce, it's hard to find off-takers for those chemicals. So at a small scale, at a food scale, we think we shouldn't have an issue. But when we get to that, municipal level that we hope to achieve, thinking about what to do with that chlorine-based chemical, it's a really difficult problem to answer. If anyone has thoughts about that,
Well, I know some
happy
people,
to, yeah.
I know some people who are worrying intensively about this problem at the very largest scale, and that's the group working on the NEOM project in Saudi Arabia, where they intend to have a ZLD, seawater desalination process with gargantuan biblical volumes of salt coming out of there. And so I think that it'll be very interesting to see what sort of ecological, sort of industrial ecosystems they're trying to create. But I do like the idea that even at a plant scale, especially for food manufacturers that have concentrated brine waste streams, rather than ROing and then shipping off truckloads of brine, you could potentially reuse a lot of the caustic for cleaning, et cetera, et cetera. Imagine pickles are green, but they could be even greener if you could, reuse your brine.
Yeah, I like it.
All right, let's check any last
catchphrase.
questions from anybody. Yeah, anybody last questions on the Q&A? Everybody, thank you so much. And there's some other really interesting fields. Shane Walker from UTEP has raised his hand. Shane and his team are working on electrodialysis metathesis and sort of other variants on ways of creating industrially valuable chemicals from the brine, quote unquote, waste. Let's hope that you're part of a future where no molecule goes to waste and everything finds a home. Margaret, thank you again very much for your time, and everybody, thank you for coming today. Appreciate everybody's attention, and follow up with Margaret, if you don't mind, just drop your email into the chat one last time so people can find you. And then everybody, on the 25th, we have another Activate Fellow, Daniel Sun, who's going to talk about various aspects of precision separations, which is the project he's working on. From all of us here, and I want to thank the NREL team, Ryan, Jennifer, for running such a beautiful show. Thank you, everybody. Welcome to 2023, and we look forward to seeing you at future NAWI events. Thanks, everybody. Bye-bye.
Thank you.